Hey guys, it's Mr. Stella talking to you from Plano West High School, Speech and Debate State. So excuse the noise if there's background noise. There's a lot of teachers here. It's about to get started in about an hour. People are coming in. Also, if there's some weird music right now, I'm sorry about that. I tried my best to take it off. This is my second video. The first one worked out really well, except that music did not know was in the background. So let's go ahead and get started. We're gonna go ahead and go over rotational kinetic energy. So this kinetic energy when something is rotating around an axis of rotation. So after kinematics, movement, motion, and dynamics forces, we went ahead and covered energy towards the end of last semester. So now we're going to go ahead and do the same thing. We've already talked about kinematics and dynamics in rotational. So now let's go ahead and talk about energy and rotational. And you'll see that everything, just like before, the big concepts and big ideas are still very much there. We're just going to put a small twist to it. So we already know that kinetic energy is 1/2 mv squared. So let's go ahead and think, what do we think is going to be kinetic energy when rotating? So rotational, and I'm not using a mouse right here, I'm using a trackpad, so I'm sorry. That'll be 1/2, and instead of m, mass is a measure of translation or inertia, so we're going to put I for rotational inertia. And then velocity, now we're going to have angular velocity, which is going to be W squared. So it's the same formula, we just have use the appropriate rotational substitutions. And we see this right here, 1/2 mv squared. And then when we apply the rotational down here, bottom, we see energy rotational equals 1/2 inertia velocity squared. So another thing that we covered when we did energy was work. The equation for work was work equals force times distance, or more appropriately, force times your change in x. And we see the same concept right here in the middle, where we have work equals, but instead of force, every time we're using force, we're using torque now. And there's my tau. So just like acceleration was net force over mass, and angular acceleration equals net torque over inertia, we do the same change right here. But instead of change of x, we have angular displacement, change in angular displacement. And that is going to be our theta right there, which is in radians. It's still going to be joules, the units are still going to be joules, but it's the same way that we're going to find it. So this is the part that I wanted to talk to you about. So far we have discussed two types. We touched on the third one, but we'll talk about that more next time. But we have GP is what they call it right here, gravitational potential energy, but it's just potential energy due to gravity. You guys know it as MGH. And then we have kinetic energy. Elastic potential energy deals with springs, but we're going to do springs when we come back from spring break. But you guys already know that one also. It's 1/2 kx squared. So it's a big idea that I want you guys to take from kinetic energy and rotational, is that An object's total kinetic energy is made out of its translational and its rotational kinetic energy. So if you guys look down here at the bottom, we see that total kinetic energy is made up of translational and rotational. So 1/2 Henry squared, 1/2 IW squared. That equals an object's total kinetic energy. And we're going to look at an example right now. So a common problem, and we're going to look at an example of this, is an object of an object and another object. They have the same exact mass, but they're different shapes. You're going down an incline, a ramp, and they ask you which one will get there first. Which one is going faster at a certain point is what they're asking you. So you guys can answer this using kinematics and dynamics, because you're going to know that the one with the smallest rotational inertia is going to have the greatest acceleration. So bigger acceleration, starting from the same initial velocity at the same amount of time. The one with the least amount of rotational inertia is going to have a bigger velocity because it has a greater acceleration. So you guys know how to answer this question with kinematics and dynamics, but let's go ahead and look at it from an energy point of view. And again, the big ideas are still there. So let's move on to a problem. Here's the problem. You have a hoop and a sphere, so like a ball and a hoop. You have this exact same mass and they're rolling down the exact same ramp, same height. They're asking you which one will have a greater velocity. How can you determine the velocity at the bottom? So I want you guys to pause this right here and think of an equation for using conservation of energy that will help you solve for the velocity at the bottom. So go ahead and pause it, talk with the person around you. Let's go ahead and do it. So hopefully what you ended up with was something like this. mgh equals your potential energy equals your kinetic energy. So what you guys have learned is that any potential energy that you have is going to transform into kinetic energy. And the exact same thing is going on right now. Any potential energy that you have is going to turn into kinetic. Except, if we break it down a little bit more, there's two kinetic energies. I really wish I had a mouse. 1/2 mv squared plus 1/2 so that energy needs to be transferred into two different kinds of energy. So if we go down here, this is what you should have started with, where the total energy, total mechanical energy, kinetic plus potential, total mechanical energy should be the same before and after. So you break it down a little bit more. Total kinetic energy is going to be kinetic translational plus rotational, and we did the same thing on both sides. It was really loud in there, so I'm hoping that this is better. Hopefully you haven't missed much because of the noise. But we see mechanical energy at the top, and they break it down, and at the very top these objects are at rest, so they don't have any rotational or translational kinetic energy. So our before energy is all potential energy. At the very bottom, they don't have any potential energy anymore. It's just kinetic energy. And it's going these objects are rotating and moving linear at the same time. So they're gonna have translational kinetic energy and rotational kinetic energy. So we have mgh equals 1/2 mv squared plus 1/2 iw2. If they ask you to find the velocity right here in the middle, then we could stop right here, because right here in the middle of the ramp there's still potential energy and on both ends. So let's see why using energy the sphere is going to have a greater velocity. So I'm going to put, I wish I can copy this instead of just spending some time here. mgh equals 1/2 mv squared So let's say that both of them have the same amount of potential energy, because they have the same mass, same gravity, same height. So the top one will be the hoop, the bottom one will be the sphere. So at this point we have the potential energy. Now which one of these objects has a greater rotational inertia, a greater I? So go ahead, pause, talk about it with your group, and see which one has a greater rotational inertia. You should have gotten that the hoop has a greater rotational inertia because the mass is farther away from the axis of rotation. So if the hoop has a bigger I, it's going to have a bigger rotational inertia. So it doesn't matter, let's say that this is 60, arbitrary number right here. That means that the translational potential, that translational linear kinetic energy is going to be 40. Now, we know that the sphere has a smaller rotational inertia. We don't know how much smaller. It could be half, it could be a third, it could just be a little bit. We just know that it's smaller in relation to the other one. So right now I'm just putting 55, but you guys, this could be 6, this could be 50, 30, 25, doesn't matter. Let's look how much is over here. This is going to be 45. So which one has a greater linear kinetic energy? It's going to be the sphere. So what's happening is that they start off with the same amount of potential energy, but that potential energy is transformed into kinetic energy. But because the hoop has a greater amount of rotational inertia, it's going to take more of that energy into the rotational kinetic energy, leaving less of that potential energy to go into linear kinetic energy. So how would you actually solve for velocity? I honestly don't think you would get a problem like this. It seems it's really long, to be honest with you. And this test has gotten more conceptual. Um, Not a whole lot of solve. Let's go ahead and talk about how you would solve for the actual velocity. Because how do you know how much energy goes into translational, how much energy goes into rotational? So let's remember this relationship over here. I'm like walking around because there's people walking around outside. It's super annoying. It's walking around me. Hopefully not ruining this video for you guys. So if we have change of x, linear displacement, and we want to find angular displacement, this is the relationship that we use. That's not a v, that's an r. So these are the relationships to go from linear, it's an r, to angular. So angular displacement to linear velocity, angular velocity, linear acceleration to angular acceleration. So what I can do is, I have two variables that I don't know when I look at these equations. I know the mass of the objects, I know gravity, I know height, but I don't know W. The top equations, looking up here, I don't know W, I don't know velocity. So there's two variables, so what I want to do is make one of those variables go away. So what I can do is velocity over R equals my W. And that's what they did. Every time they had a W, like right here and over here, hopefully you can see my mouse, they plugged in V over R. And then each of these objects has its own equation for moment of inertia, the hoop being mr squared, and then the sphere being 2/5 mr squared. They plugged that in too, and then they just solved for V. So last year I did the problem. I had the problem where I taught my kids physics, not so much conceptually, but really concentrated on solving problems that had numbers, and it really bit me on the butt. I got a lot of 2s. So I'm hoping this semester to go over how to solve these problems, give you in passing how to solve them in case they do pop up, but really betting that they won't pop up. So, sorry, when you look down here, you see that the velocity is 1.2 times bigger on the sphere than the hoop. So going with energy, this slide really gets the big idea. Both the sphere and the hoop started with the same potential energy. And that potential energy is going to convert into kinetic energy at the bottom where there is zero potential energy. The hoop with the greater moment of inertia, greater I, is going to take a greater amount of that total kinetic energy that came from the potential energy to make it rotate. So it's going to take a lot of that potential energy, leaving very little or less kinetic energy available for translational motion, for linear motion. So the sphere has a greater translational velocity. So I'm going to make another video later on today for angular momentum, but I'm going to send you a couple of problems right now, and then we're going to go ahead and talk about those problems. Hey guys, so I want you guys to look at this problem. So it's very similar to what we've been doing past couple minutes for you guys, an hour ago for me. So two objects are released from rest at the top of a ramp with the same dimension, so they have the same height. The sphere rolls down one ramp without slipping. So when you guys hear without slipping, I want you guys to just think it's rolling. That's all it is. Without slipping means that it's rolling, has rotational motion. So the small object slides down the other ramp without friction. So it's just sliding down, no friction. So when you think no friction, you have to think mechanical energy is conserved completely. So which object reaches the bottom of the ramp first and why? So go ahead and take a moment, pause it, talk about it with your people, and see what you think the answer is. So let's look at all the answer choices. The sphere, they're saying A says that the sphere reaches the bottom first because it gains rotational kinetic energy, but the block does not. Which is true. The sphere gains rotational kinetic energy, but the important thing is which one is going to gain the most linear kinetic energy. That's the one that's going to reach the bottom first. So the sphere, because it gains mechanical energy due to torque exerted on it, the block does not. So yeah, it has torque on it. Friction is supplying the torque that's making it spin, but the other one is also gaining energy, mechanical energy. The block, because it does not lose mechanical energy due to friction, but the sphere does. So that one, very true right there. Everything that thing says is true. It does not lose mechanical energy due to friction. Yeah, the other one does. But that's not the reason why it reaches the bottom. It's correct, but not answering the why. So we look at D. The block, because it does not gain rotational kinetic energy. One moment. The block, D, because it does not gain rotational kinetic energy, but the sphere does. That's the reason why. All the potential energy, they all have the potential energy, but in the sphere, some of that potential energy converts into rotational energy, leaving a smaller fraction for linear kinetic energy. But the block does not gain rotational energy. It only gains kinetic translational energy. So it's going to have a bigger amount of linear kinetic energy. More kinetic linear energy means a bigger linear velocity. So that's why the answer is D at the very bottom. Let's look at this problem. This problem has two solutions. We must select both. If the answer is AB and you put AC, you get no credit. You have to put both correct answers. So we have a uniform plank is placed with a pivot on its center. A block is placed on the plank to the left of the pivot as shown in the figure above. A student is asked to place a second block of greater mass on the plank so that it will balance when horizontal. Which of the following quantities are needed to determine where the second block should be placed? So what do they want this thing to do? Let's think about it. Pause it, talk about the answer, what you think is the answer with someone around you, and then come back. Pause it. Alright, I'm about to go over the answer. So we want this object to balance when horizontal. So if it's not rotating in either direction, that means that I want the net torques to be in balance. I want the net torque to be 0 so that there is no angular acceleration in either direction. So if I want my net torques to be 0, the torques in either direction must be balanced. So I want tau to equal tau, one to the left, one to the right. So we have force times the radius, force times the radius. So I ask myself, what is the force that's causing this thing to rotate? Well, it's not a wheel where it's friction. It's going to be gravity. So we have, that's an M, mgr equals mgr. The weight of these boxes is the thing that's causing it to rotate. So what do I need to make these things equal to each other? I need to know the mass of each object. So that's why we have B. And if I want to know where, well, let's not forget what I'm looking for. Determine where the second block should be. I'm solving for this R, that's what I want to know. So if I want to know what this R is, I'm going to have to know every other value here. So I need to know this R over here. The distance from the pivot of the left block. The answer is going to be D. If you guys have any questions about anything throughout this video, the notes part, go ahead and feel free to send me a message. I'll answer it. I promise you guys. I want you guys to succeed. So let's look at problem 8. A disk is initially rotating counterclockwise around a fixed axis with angular speed W0, initial angular. At time t equals 0, the two forces shown in the figure above are exerted on the disk. If counterclockwise is positive, which of the following could show the angular velocity of the disk as a function of time? So take a moment, talk to the person around you, and go ahead and answer this question. Pause it, talk about it, then come back. So we have two torques. We have 20 newtons in one direction, we have 40 newtons in the other direction. So the net torque is going to be towards the right hand side, towards clockwise, and it's going to be a net torque of 20. So if the object is rotating to the left, but there's a force to the right, what's going to happen? Well, think about it in linear terms. If you have a positive velocity and you have an acceleration towards in the opposite direction, the object is going to start slowing down. So it's still moving the same direction. You have a positive velocity, negative acceleration right here. So the object's still moving the positive direction, but it's slowing down. So we can go ahead and cancel out A and B, because it's initially rotating counterclockwise and tell you that that's positive. So it should start in the positive direction, and only C and D do that. And we do see that initially they're slowing down. So if we have a velocity towards the positive and acceleration towards the negative in the opposite direction, this object's going to eventually come to a stop. Once it comes to a stop, it's going to start speeding up in the opposite direction because that acceleration is still there. So we see that it's going to start changing directions, and they're going to start speeding up. Because think Just picture this in your head. We have this object, this wheel, and it's rotating to the right, and all of a sudden you start pulling on it. What's going to happen? It's going to start slowing down till it comes to a stop, and then it's going to start speeding up in the direction that you're pulling. And that's why the answer is C. It's going to slow down, and it's going to start rotating the opposite direction, which it was, and then it's going to start speeding up in that direction. So the answer is C.